Welcome to our Foundation Mastery Method for Calculus Foundation. In this lecture, we'll be talking about limit, derivatives, integrals, and their applications in real life. First, the limit concept. Let us take a function or expression, you can say, limit x approaches 1 to x plus 3. This one is very straightforward. We can plug x equals 1 and see what happens. When you replace x by 1, you get 2 times 1 plus 3, which is 5. Next, we are taking limit x approaches 1, x squared plus 5x minus 6 over x minus 1. So in the numerator, I'm getting 1 plus 5 minus 6 divided by 1 minus 1. So 1 plus 5 minus 6 is 0, and 1 minus 1 is also 0. So we get 0 over 0, which is known as undefined form. So that means we have to do some manipulation on this expression and then see if we can find a nice answer. So algebraic manipulation meaning is, let's try to factor the numerator. And you know the trinomial factoring, x squared plus 5x minus 6 will come out like x minus 1 times x plus 6, and in the denominator we have x minus 1. And since we are taking x approaches 1, not exactly 1, so x minus 1 we can cancel out, and we get the reduced form like this. Now this one is very similar to the first example. If you replace x by 1, then 1 plus 6 is 7, and that's the limit. Graphical form. Suppose we have a graph given as a piecewisely defined, and some values are known, given with the big circles as you see, and the white circle meaning is the point is not defined at that position. So we are interested to see what is the limit of the function when x approaches 1. As you see on the graph, when x approaches 1, you can see a jump here. So limit does not exist. Next, we want to see what happens if I go little right side of 1. When you go to little right side of 1, it is actually on the second line you see here with 2 open dots. So 1 plus actually giving me here, which is negative 1 according to this graph. So the right hand limit is negative 1. And then we want to see what is the left hand limit, which is 3. And by definition also, you have seen the right hand limit, left hand limit, they are different. So we call it a jump. And that's why limit at x approaches 1 does not exist. We check couple of other values. What happens limit at 3 plus? So 3 plus meaning is, if you look at the scale, 1, 2, 3, here again you see jump. So limit does not exist. But if you go 3 plus, then you have this one, which is negative 3. If you want to go 3 minus, that one is here, which is 2 units. And that's why you're saying limit at 3 does not exist. And next we want to check what happens limit at negative 2. As you see on negative 2, the graph is continuous. It doesn't have any issues there. So then that limit is, y value is 0. So limit is 0. Next, we are going to check the function value. We are given a function in a rational form, 3x minus 2 over x plus 3. We want to determine what is the value of the function at negative 3.01 and at negative 2.99. And in this case, we also investigate what happens when x is negative 3. And as you see in the function, when x is negative 3, x plus 3 is 0, which makes the function undefined, and a numerator is other than 0. So clearly we have a vertical asymptote at x equals negative 3. So you can use this most graphing calculator, and then you will see that limit does not exist, and we will see the graph here. So at negative 3, we have a vertical asymptote, as you see here. And now we just try to find the value of the function at this. You can grab a calculator, or even in your Desmos, you can ask for that point when x is negative 3.01, and you will see it 1103. And then the next one at negative 2.99, it will give you negative 1097. Next, we are talking about average rate of change between 2 points. So the plain idea is like this. If we are given a function 2x squared plus 1, and we are given at x equals 3 and x equals 5. So we are using as a closed interval in here for x values. So then the average value is, the function is evaluated at 5 and 3 and take the difference, and then 5 minus 3 in the denominator, which is basically the rise over run. So average rate of change, basically the slope of the line passing through 2 points where x is 3 and x is 5. So we are getting this. Now we need to plug x equals 5 first to get f5 and 3 for f3. So you see f5 is 2 times 5 squared plus 1, which is 51. And f3 gives me 2 times 3 squared plus 1, which is 19. So we plug the values here and simplify. We get 16. We'll take some couple of more. Now, in a table, there's a different question though. We are given a table with t values and st values. We are asking find the average rate of change on 3, 6. So we clearly understand that I have to find what is S6, which is 22, and S3 is 10. And then you can write the formula here. So as you see, at t equals 3, we have S is 10, and at t equals 6, we have S equals 22. So the average rate of change on 3, 6 is this difference, S6 minus S3 over 6 minus 3. We plug the values and simplify. So final answer is 4. We'll be taking another example. Let me take the same table, but we are saying that this table shows the cost function CT in millions of dollars. But here I'm writing ST, you can consider this an SCT. And that one is per year, where T is the number of years since 2015. So we have to pay attention on since 2015. What does it mean? So now we want to see that T is the number of years since 2015. So we want to see what is 2015. And we'll find average rate of change between the years 2016 and 2020. So as we said, since 2015, so that means at the year of 2015, my T is 0. So then definitely for 2016, T will be 1, and 2020, T will be 5. So we are interested to find average rate of change, S5 and S1, between 2016 and 2020. Okay. So we are getting 24 minus 21 over 4 and simplify further.